Hello, everyone. I'm Zhao Zhenyu from Shandong University of Technology. I'm honored to have the opportunity to introduce my recent research work here. This work was done with Yikai, Jiaxian Zheng, and Dou Zhihong. It has been accepted and published online by the journal Applied Numerical Mathematics. I will only introduce the general idea framework here. You can check the paper online for specific details. If you have any question, please contact me. The report is divided into three parts. First, I will introduce the motivation of this research, and then further introduce the edge detection methods based on Fourier extension, which is also the main innovation of this research. Finally, the result of numerical experiments are given. Well, let's move on the first part of this talk. What is numerical differentiation? It means that a function f belongs to HP. A state is generally obtained by measurement. We actually have the perturbed state f dirt. We assume that they satisfied the following relationship, where dirt is the noise level. Our goal is to obtain an effective approximation f dirt of f through the date f dirt, so that the equation 2 holds. Numerical differentiation is a typical air-posit problem. That is to say, arbitrary some small error in the input state may cause huge errors in its approximate derivatives. The numerical differentiation arises in many practical problems, such as image processing, identification, the height conduction equation, and the Abel integral equation, etc. Many scholars have studied the numerical differentiation problem, some of which are listed here. The result obtained by these studies will basically not exceed the result given by equation 3. In other words, the convergence rate of the derivative approximation will not exceed 10 to the power of p minus k over p. If the function fx is smooth enough, our method give good numerical result. However, in many cases, the function f does not exhibit sufficient regularity. Function f may be piecewise continuous or continuous with piecewise continuous derivatives. If we applied numerical differentiation method directly to such kind of function, large error may occur at the discontinuity point of fk. Therefore, it's important to determine the location of these discontinuity points. Now, let's recall the edge detection method based on Fourier coefficients. For 2 pi periodic piecewise smooth function with finitely jump discontinuities, we define jump function as following. In smooth regions, square brackets G equals to 0, and at discontinuities, square brackets G is the value of the jump. If the Fourier series of G is given as equation 5, then the following modified partial Fourier sum can be used to detect the edge of G, and we have the following lemma. That is to say, the modified partial Fourier sum converges uniformly to the jump function. For the given data after our goal is to detect the discontinuity point of G equal Fk. It should be noted that the function f is generally not periodic, so we need to use Fourier extension to construct approximation. That is to say, regard the function f defined on the interval -1 to 1 as the part of the periodic function defined on -pi to pi. Therefore, we define the following operators. If Fk is not continuous but piecewise smooth, then it can be deduced that f belongs to hk plus bit. We consider the following mathematization problem, where f is the regularization parameter, and u after can be obtained by solving the following equation. And we can obtain the convergence result as the equation 30. Then we can use TF30K for edge detection of Fk. After obtaining the information of the discontinuous points, we can divide the interval into several sub-intervals. The function is smooth in each small interval so that different methods can be used for numerical differentiation. You can refer to the description in the paper for the specific method. I will not repeat it here. Now, let's take a look at the numerical example. These two examples are the case where the first order derivative is discontinuous. These two figures are their function images, respectively. From the figures, we can roughly see the location of the derivative discontinuous points. But this becomes difficult when the data is disturbed. These figures are the result of edge detection and different noisy level, and we can see that the method is effective. Here are the calculation result of the first order derivative. We compare the case without edge detection. And we can see that the accuracy of the method has been effectively improved. The next example is the case of second-order derivative discontinuity. From the function image, it can be seen that the information of the discontinuous points becomes more difficult to detect. From these figures, it can be seen that the method for edge detection is still effective at this time. Similarly, from the result of numerical differentiation, it can be seen that effectively identifying discontinuous points can improve the accuracy of problems. That's all. Thank you for your attention.